Hello everybody, welcome into another lesson. So today we are going to talk about planes in space. So we're going to find equations of planes. And the first set of problems is going to read a lot like, find the equation of the plane through the given point and normal to the vector or line. Well, you have some point P where you have x sub 1, y sub 1, z sub 1, where the plane passes through. It's one of the points on the plane. Now, the normal vector is always perpendicular to the plane. When we were talking about lines, doing equations of lines, we used a vector parallel to the given vector. To do planes, you got to do perpendicular to the given vector. And in a little bit, we'll go over how to find the normal vector, but we're going to start off easy where the vector is given to us. But just like we were dealing with lines, the normal vector are your direction numbers. Those are your direction numbers, A, B, and C. So to get the standard equation of a plane, you'll take your direction number for your x component, A, times x minus x sub 1, plus that B times your y minus y sub 1, plus c times z minus z sub 1, set that equal to 0. Then when you distribute and simplify everything, you should get the general standard form of the equation of a plane, ax plus by plus cz plus d equals 0. So let's go over some of these examples here, where first the normal vector is given to us. I'm going to put up the wording of the problem also, so you have that. Alright, so find the general form of the equation of the plane passing through the given point and normal means perpendicular, since we're going to use a normal vector. So for these purposes, normal means perpendicular, and normal to the given vector or line. Alright, so we're going to find the general form of the equation of a plane passing through the given point, which will be P, in normal to the given vector or line. So point P in this particular example is going to be the point 2, 1, 2. The normal vector, so the normal vector we're considering is simply I, which we know in component form I equals 1, 0, 0. Alright, so we're going to find the equation of the plane passing through point P, which has the order triple 2, 1, 2, and normal to the given vector, which is 1, 0, 0. Well, if the vector's given to you, it's actually really easy, because all you're going to have to do is take your direction numbers from your normal vector. So that's going to be, your A is 1, so you would take 1 times x minus your x sub 1 coordinate from point P, which would be 2, plus you'll take your second component, which would be that 0, times your y minus your y coordinate of your point, which would be 1, plus your third component of the vector, which would be 0 times your z component of the vector, so z minus 2, you would set that equal to 0. Well, good news is these two terms go to 0, so all you have is 1 times x minus 2, which to get the final form of the equation, you'll just get x minus 2 equals 0. So the general form of this particular equation is just x minus 2 equals 0. That would give you the equation of this plane, y minus 2 equals 0. All right. Let's see what we got now. This particular plane is going to go through the point 1, 0, negative 3, normal to the vector 0, 0, 1. So this plane goes through point P, which has order triple 1, 0, negative 3, normal to the vector 0, 0, 1. Well, that 0, 0, 1, those are our direction numbers. So to start with, take your first component, that's 0, times the quantity of your x minus 1 from point P, plus take your 0 times the quantity of y minus 0 from point P, plus take your 1 from the normal vector, times the quantity of z minus that negative 3, that actually turns into z plus 3, set all that equal to 0. Good news is the first two terms go to 0, so your last term, you're just going to distribute a 1. The equation of this plane would be z plus 3 equals 0. So you'll get an equation of a plane with z plus 3 equals 0. All right. Now let's add some other vectors in. Let's actually do a little bit more this time with our vectors. Alright, so this plane passes through point P, which has the order triple 5, 6, 3. The normal vector is going to be negative 2, negative 1, actually negative 2, positive 1, minus 2. Alright, so we want to find the equation of this plane passing through point P. 5, 6, 3 is the order triple, and normal to the given vector negative 2, 1, negative 2. Again, this normal vector, those are your direction numbers. So we'll take that x component, that negative 2, times the quantity of x minus that 5 from point P, plus we'll take that 1 times y minus 6 from point P, and then plus that negative 2, which would be minus 2, times z minus 3 from point P, set all that equal to 0. So now we just distribute, you would get negative 2x plus 10 plus y minus 6 minus 2z plus 6. And then we simplify all this, you would end up getting negative 2x plus y minus 2z plus 10 equals 0. So that would actually be the equation of this plane in standard form, would be negative 2x plus y minus 2z plus 10 equals 0. Let's do one more like this, and then we're going to be given lines instead of a normal vector. Alright, so point P this time. They take it easy. Point P is 0, 0, 0, right at the origin. So the plane goes through the origin. the normal vector is going to be 0, -3, 5. So this plane goes through point P, which is at the origin, normal to the vector given 0, -3, 5. So first, again, pull out your direction numbers from that vector. So take 0 times the quantity, since that's your x component, you'll take it times x minus x sub 1, which is 0, plus you'll take that -3, so in this case minus 3 times the quantity of y minus 0, your y coordinate of the order triple, plus 5 times the quantity of z minus 0 from the order triple, set it all equal to 0. First term goes to 0. The minus zeros inside the quantities, that would just leave the variables. So you do your distributing, you would just get -3y plus 5z equals 0. That would be the equation of this plane in standard form. You would get -3y plus 5z equals 0. Alright, so we've been given the normal vector and we've been given a point it passes through. Now, we also will have times we're not given the normal vector, but it's going to be normal to a line instead. So the line in this case, we're going to switch it up to some, with the plane being normal to some lines. So point P would be at 2, 0, 0. The line it's normal to is x equals 3 minus t, y equals 2 minus 2t, and then z is equal to 4 plus t. Alright, so we want to find the general form of the equation of the plane passing through this point P, which is at 2, 0, 0, and normal to the given line, x equals 3 minus t, y equals 2 minus 2t, z equals 4 plus t. Okay, so this is a lot like yesterday's lesson in the fact that, for one, you have the next best thing here with the line. Because remember, with the line, your coefficients of t are your direction numbers. So you just ignore the constant term for each of these variable equations. You look at the coefficients on the t, that would be your normal vector for this plane. So we actually have our normal vector now. Coefficient for the x term is -1 on the t. Coefficient on y is -2. Coefficient on the z term for t is +1. So now we've identified our normal vector to be -1, -2, 1. We can go ahead and start finding the equation of the plane. So take your x component of that normal vector, the -1, times the quantity of x minus that 2 from point P, plus -2, which would be -2, times y minus 0 from point P, plus 1 times that z minus 0 from point P, set all that equal to 0. Just to go ahead and distribute, you'll end up getting -x plus 2 minus 2y plus z equals 0. And in order for this to be in standard form, we need to have the variable terms next to each other. So we just got to rearrange some terms. You would get -x minus 2y plus z plus 2 equals 0 would be the general form of the equation for the plane passing through the point 2, 0, 0 and normal to the given line. Let's do one more like this, then we're going to shift gears a little bit. Actually, let's keep that format because we're going to have lines again. point P is going to change, of course. So point P is located at 0, 0, 6. The line that this plane is normal to is x equals 1 minus t, y equals 2 plus t, z equals 4 minus 2t. Alright, so we want to find the general form of the equation of the plane passing through the given point and normal to the given line, where that point is at 0, 0, 6. The line is x equals 1 minus t, y equals 2 plus t, and z equals 4 minus 2t. Well, we may not have the normal vector, but we have the next best thing. We have, again, if you have your coefficients of t, those are your direction numbers, so you actually can get the normal vector from those direction numbers. Take your coefficients of t for each of your components. So on the x1, you get -1 for the coefficient on t. For the y term, you get +1 for your coefficient of t. And then for the z term, you get -2 for your coefficient of t. So from there, you've just derived your normal vector. Now we can go ahead and find that equation. So go ahead, take your x component of the normal vector, that -1, times the quantity of x minus 0 from point P, plus 1 times the quantity of y minus 0 from point P, plus -2, so that'd be -2 times z minus 6 from point P, is equal to 0. So go ahead and do your distributing. You would end up getting -x plus y minus 2z plus 12 equals 0. And in fact, that's all you got to do. You don't even have to move any terms around. It's literally set up in standard form for you. So the equation of this plane should be -x plus y minus 2z plus 12 is equal to 0. Alright, so we've had it pretty easy so far, where the vector or the line that contains that vector has been handed to us. Now it's going to get marginally tougher because we're going to be given 3 points that the plane passes through. And we're going to have to come up with a vector and take a point. So let's change gears now, where we're going to be given the equation of a, we're going to have to find the equation of a line passing through the 3 points. So find the equation of the plane passing through points P, Q, and R. So we're going to have points P, Q, and R where we need to find the equation of the plane. So point P in this case would end up being, let's see, point P is the origin. Point Q is going to be at 1, 2, 3. Point R is going to be at -2, 3, 3. Alright, so we need to find the equation of a plane passing through these 3 ordered triples. P at 0, 0, Q at 1, 2, 3, R at -2, 3, 3. So it might help if we plot the points to understand what exactly we're looking for. Let me change color. So here's point P, right at 0, 0. Point Q is going to be at 1, 2, 3, right about here. Here's point Q. Point R is going to be at -2, 3, 3, -2, 3, 3. So here's point R. And if you look at this here, so you have points P, Q, and R. We want to find the equation of this plane, all right? Let me quit dropping stuff. You know, let me make this a little bit bigger here, just so we can see. I think we can kind of warp the dimensions a bit in this case. So here's going to be, we said Q, here's going to be R. There you go. Now we got something we can see a lot better, right? All right, so there's plane PQR. What you need to do first is you need to find a vector u and a vector v. And there's a reason for that. So if you're given 3 points, find a vector u and a vector v. We'll call vector u, which would be PQ. And then we'll call v would be PR. So pick a point, pick one point, and then you'll go from that point to one of the other points, and then you'll go from that same point to the other point to get your 2 different vectors. That's how this works. I think it's going to be easiest to deal with PQ. Vector PQ we'll call vector u, vector PR we'll call vector v. So let's get these vectors here. So vector PQ, we're going to call that vector u, is going to be 1 minus 0 is 1, 2 minus 0 is 2, 3 minus 0 is 3. So we got vector u being 1, 2, 3. Now we need to find vector PR, which will be our vector v. So P to R, so that would be a vector of -2, 3, 3. Alright, so great, we got our vectors. So what does that mean? In order to find the equation of a plane, we need to find a normal vector, which will give us our direction numbers. In order to find that normal vector, what do we remember from the cross products lesson? The cross products lesson is always perpendicular to the 2 original vectors that you took the cross product of. So in other words, we need to take the cross product of vectors u and v. That'll give us the equation of our normal vector. So the normal vector itself is equal to the cross product of, that's going to be vector u and vector v, which, taking the cross product, will have I, j, k, and then your components of vector u would be 1, 2, 3. Vector v would be -2, 3, 3. Now we just got to set up 3 2x2 determinants. So this will end up being I times, strike out the column and row that it's in, that would be 2, 3, 3, 3, minus j, times, strike out the column and row it's in, you would get 1, 3, -2, 3, plus k, times, strike out the column and row, you get 1, 2, -2, 3. Now let's do the determinant work here. You would end up getting I times 2 times 3 is 6, minus 3 times 3, that's minus 9. Then you'll have minus j. Then let's see, 1 times 3 is 3, and then -3 times -2, that's going to be positive 6 plus k times, all right, 1 times 3 is 3, minus 2 times negative 2, that's plus 4. So when you simplify this, you'll end up getting negative 3i minus 9j plus 7k. That is your normal vector, negative 3i minus 9j plus 7k. Alright, so if you need to see how I got the cross product, please feel free to rewind this and go back. For space sake, I'm going to erase all this determinant work and rewrite my normal vector in component form. Because the determinant gives you a linear combination, it might be easier to write it in component form. So the normal vector is negative 3, negative 9, 7. Alright, now we found our normal vector. And just like the equation of a line, the equation of a plane is also not unique if you have multiple points. You can pick any single one of these points and you should come up with the same equation. So let's go ahead here, we'll pick point P. Just for simplicity's sake, we'll pick point P, being 0, 0, 0. So we'll take our direction number from the normal vector for our x. That would be negative 3 times the quantity of x minus 0 plus negative 9, so minus 9 times y minus 0 plus 7 times z minus 0. All that's equal to 0. Now just do some distributing. You should end up getting negative 3x minus 9y plus 7z equals 0. So you should end up getting negative 3x minus 9y plus 7z equals 0. And if you pick any one of these points, you should arrive at the same result. So keep that in mind. Alright, let's do some more here. Let's erase this. Let's do a couple more of these where we're only given 3 points. All right. So point P is going to be at 4, negative 1, 3. Point Q would be at 2, 5, 1. Point R is going to be at negative 1, 2, 1. All right, so we got to find the equation of the plane that passes through point P at 4, negative 1, 3, point Q at 2, 5, 1, and point R at negative 1, 2, 1. Why don't we again go ahead and plot this for illustration purposes. So P is at 4, negative 1, 3, so that's going to be about up here. There's point P. Point Q is going to be at 2, 5, 1. Right about there is point Q. And then point R is at negative 1, 2, 1. There's point R. Alright, we have a very thin little plane there, but it is a plane. There's plane PQR, pick any point you want. Traditionally, we usually start with point P when doing these. We traditionally start with point P. So let's go ahead here. We want to probably, if we're going to start with point P, let's find vector PQ. Well, vector PQ, we'll call that vector U. So here's your vector U. And then we'll also have PR. We'll call that vector V. So here's your vector V right there. Alright, so let's find these vectors. Vector U, if we take the vector from P to Q, 2 minus 4 is negative 2. 5 minus negative 1, that's 5 plus 1, which is 6. 1 minus 3 is negative 2. So vector U turns out to be negative 2, 6, 2. Now let's find vector V by finding the vector from P to R. So negative 1 minus 4 is negative 5. 2 minus negative 1 turns into 2 plus 1, which is 3. 1 minus 3 is negative 2. Alright, so now we have vectors U and V. Well, again, in order to get our normal vector, we need a vector that's perpendicular to both vectors U and V, which is the normal vector. The normal vector, again, is taken by finding the cross product of these two vectors. So vector U and V will take the cross product of all that. So set up your cross product. You'll have I, J, K in the first row. And then, let's see, the first vector U would be negative 2, 6, negative 2. Vector V would be negative 5, 3, negative 2. So let's go ahead and start doing the determinant work. You'll have I times the resulting 2 by 2 determinant of 6, negative 2, 3, negative 2, minus J times, let's see, you would end up getting negative 2, negative 2, negative 5, negative 2, plus K times negative 2, 6, negative 5, 3. Alright, let's do the determinant. So you would have I times the quantity of 6 times negative 2, that's negative 12, minus negative 2 times 3, that's actually plus 6, minus J times the quantity of negative 2 times negative 2, that's positive 4, minus negative 2, so plus 2 times negative 5, that's minus 10, plus K times negative 2 times 3, that's negative 6, times, sorry, minus 6 times negative 5, that's plus 30. So to simplify, you would end up getting negative 6I minus 6 times negative j, that's plus 6j, and then negative 6 plus 30, that's 24, so plus 24k. So there's your normal vector, negative 6i plus 6j plus 24k. And like before, I'm just going to erase this and write my normal vector up here in component form. Alright, so if we take this negative 6i plus 6j plus 24k and write it in component form, you'll end up getting the normal vector negative 6, 6, 24. That would end up being your normal vector. Alright, so there's your normal vector, negative 6, 6, 24. From there, we have everything we need to start plugging and finding the equation of a plane. And traditionally, we go with point P for our x sub 1, y sub 1, z sub 1. So let's take that direction number of negative 6 for the x component times the quantity of x minus 4 plus that 6 for the y component times the quantity of y minus negative 1, so that'd be y plus 1, plus 24 for the z component times z minus 3, set all that equal to 0, you would end up getting negative 6x plus 24 plus 6y plus 6 plus 24z minus 72 is equal to 0. And then we simplify this, you should end up getting negative 6x plus 6y plus 24z. All right, and then 24 plus 6 is 30, minus 72, that's minus 42, equals 0. So the equation of this plane in standard form would end up being negative 6x plus 6y plus 24z minus 42 equals 0. All right, so we have found the equation of the plane now through if you have 3 points. We're going to shift gears and actually temporarily get a little bit easier. We're going to be given the equation of a plane, we just need to graph it. And those are actually super simple. There's a real easy trick for it. Alright, so let's graph some planes here. So let's say you have the plane x plus 2y plus 3z equals 6. So this could still be in standard form. There's debate between standard form being with the D on the left side or the right hand side. Either way is acceptable depending upon your professor or your textbook. But you have x plus 2y plus 3z equals 6. The easiest way to plot your plane, to graph your plane, is to find your intercepts. So let's start with finding the x-intercept. Now, I know in 2D, to find the x-intercept, you would always set y equal to 0. In 3D, you're going to set both y and z equal to 0, and then you'll get your answer for x. If we do that, you would get x equals 6, which would be at the point 6, 0, 0. So now I'm going to go ahead and plot that point 6, 0, 0, which would be right about here. There's 6, 0, 0. So 6, 0, 0. And of course, now we can find the y-intercept. The y-intercept can be found by setting x and z equal to 0. If you do that, you would get 2y equals 6, which would give you y equals 3. So your y-intercept will be at the point 0, 3, 0. So let's find that. That's about right here. So there is 0, 3, 0. In fact, I'm going to go ahead and start connecting these points. Then, of course, we need to find the z-intercept. The z-intercept, you guessed it, you're going to set x and y equal to 0 to find your z-intercept. If you do that, you'll get 3z equals 6, which would give you z equals 2. So the z-intercept will be at the point 0, 0, 2. So let's go ahead and plot 0, 0, 2. That's about right here. So now we can just connect the points. There is 0, 0, 2. And there's your plane. Just by connecting your intercepts, you have gotten the graph of your plane. It makes life a lot easier. Let's do one more for graphing a plane, then we're going to move on to the final topic today, which is finding the line of intersection of two planes. Alright. In fact, I'll even keep this up here so we know what we're working with. Of course, we're just going to have different answers. So this plane is given to us by the equation 2x minus y plus 4z equals 4. So the equation of this plane is 2x minus y plus 4z equals 4. Again, the best way to graph a plane is to find your intercept. So let's find the x-intercept by setting y and z both equal to 0. You would just get that 2x equals 4, which would give you that x equals 2. So your x-intercept is at the order 222, 0, 0. So now let's go ahead and plot that. So here is roughly 2, 0, 0 right there. And then we need to find the y-intercept. Well, we'll set x and z equal to 0. You would just get that negative y equals 4, which would give you that y equals negative 4. So the y-intercept would be at 0, negative 4, 0. So that would put you right about over here for your y-intercept. That would be at 0, negative 4, 0. And I'll go ahead and start connecting the x and y-intercept there. And of course, let's find z. So to find the z-intercept, set x and y equal to 0. Well, you'll end up getting 4z equals 4. That would give you z equals 1. So your z-intercept is going to be at 0, 0, 1. And then we just plot the z-intercept, which is right about here. So there is 0, 0, 1. And now just connect your points, and there's your plane. There is going to be your plane with those three intercepts. So by and large, that's actually the best way to do these. Alright. I do have one more topic today. That's finding the line of intersection of two planes. And it involves the use of system of equations. That's exactly what it does. So let's just say, for example, you have 3x minus 4y plus 5z equals 6. And then you have x plus y minus z equals 2. Now, this is definitely a system of equations. Well, let's go all the way back to when we did systems of equations. If you had less equations than variables, you always had infinitely many solutions, right? Well, what does that infinitely many solutions mean geometrically? That means that it's a line. If you have infinite points, that's a line. A line goes through infinite points in two directions. And also, when we talk about the intersection of a plane, we look at two planes that intersect. Their intersection is always a line. And that's actually a postulate all the way back from geometry, that two planes intersect in a line. So the idea is you're going to solve this system and get the parametric equations of a line where these two planes intersect. So pick your variable for elimination. If we want to pick our variable for elimination, well, why don't we pick, let's go ahead and pick y. No, actually, let's pick x. I think it's safe to stick with x. So we're going to multiply the second row by -3. This would turn into 3x minus 4y plus 5z equals 6. Multiply the second row by -3, so you would get -3x minus 3y plus 3z is equal to -6. Now all we have to do are add these two rows together. You'll at least temporarily eliminate the x variable. So this would simplify into -7y plus 8z equals 0. Alright, so what the heck are we going to do with that? You just have -7y plus 8z equals 0. My suggestion is solve for y. All you're going to be able to do is get the variables separated. You'll end up getting -7y equals -8z, which would end up giving you y equals 8/7 z. Okay, that's great. So we have y equals 8/7 z. And what we can do now, since we've solved in terms of z, z is just z, y is 8/7 z. Let's stick both of these, the z itself and the y equals 8/7 z, into one of these two equations and get an answer for x. So x plus our y is 8/7 z minus z equals 2. Well, this is going to simplify into x plus 1/7 z equals 2, which would simplify further into x equals 2 minus 1/7 z. Now, in general, we would like to get parametric equations. In order to get parametric equations, it's actually quite simple. It's really very simple. All you need to do is let z equal t. If you let z equal t, then you'll have your parametric equations. You'll just have to plug that t in for your y and x equations. So your parametric equations ends up being, let's solve for, we got z equals t. This would have to mean then that y equals 8/7 t. But what about x? So x would equal 2 minus 1/7 t. So now that you have your answer for parametric equations, you'll have x equals 2 minus 1/7 t, y equals 8/7 t, and then z equals t. Those would be your parametric equations of the line of intersection for these two planes. And since we can see your direction numbers are not 0, we could even find symmetric equations if we really wanted to, but I think we'll just stick with parametric for today. So what you're going to do, solve your system. I would definitely eliminate x first, and then that'll leave you with one equation with y and z. Solve for y in terms of z, and then put the z and the y in terms of z into one of the original equations. You'll get a value for x in terms of z, and then by default let z equal t, and then just plug those in for your other equations. You'll end up with parametric equations. Really pretty simple. Let's do one more for two planes intersecting. Whoops. We want to find the parametric equations for a line that intersects two planes. Alright, so we have 2x plus 4y minus 2z equals 1. negative 3x minus 6y plus 3z is equal to 10. So we have 2x plus 4y minus 2z equals 1. Negative 3x minus 6y plus 3z is equal to 10. Well, again, we know that we only have two equations with three variables, so we're finding the line of intersection that these two planes intersect in. So what we're going to do, again, I always suggest you can eliminate any variable you want. It's just traditionally we like to eliminate x. So what I'm going to suggest to eliminate x, multiply your top equation by negative 3. If you do that, you'll get negative 6x minus 12y plus 6z equals negative 3. And then multiply your bottom equation by 2. You know what? I don't know why I multiplied by a negative in the top. Silly me. I mean, I could have and just subtracted, but let's multiply the top equation by positive 3, because really I just want to add the two equations together. So positive 3, that would give me 3x plus, that'd give me 6x plus 12y minus 6z equals 3. And then multiply the bottom equation by 2, you'll get negative 6x minus 12y plus 6z equals 20. Something very interesting is about to happen here. Let's go ahead and add these two equations together. So you add these two equations, well, all your variables are going to eliminate. You'll just get 0 equals the right-hand side of 23. Well, we know that's not true. 0 doesn't equal 23 ever, right? Do we remember from systems of equations, when you get a false statement, that means there's no intersection. There's no intersection, so what does that mean geometrically? If they don't intersect, they're parallel. That means these two planes actually are going to run parallel to each other. If they don't intersect, they got to be parallel. That's the only other way. So we just uncovered two parallel planes. Let's actually do one more with a point of intersection. I would really like to try to do that. Alright, x minus 3y plus z equals negative 2. Two x, is that plus or minus? Plus 5z is equal to negative 3. Alright, so we have x minus 3y plus z equals negative 2, 2x plus 5z equals negative 3. Again, we have less equations than there are variables, so we're going to find the line of intersection for these two planes. I definitely suggest, once again, eliminate your x variable. So all we need to do in order to do that is multiply the top equation by negative 2 and then add the two equations together. So you multiply the top by negative 2, you'll get negative 2x plus 6y minus 2z equals positive 4. And then keep your bottom equation. You'll have 2x plus 5z equals negative 3. Now we can just add these two equations and eliminate the x. Negative 2 plus 2 is 0. 6y plus 0, that gives you 6y. Negative 2z plus 5z, that's plus 3z, is going to be equal to 4 minus 3, which is 1. So you're left with 6y plus 3z equals 1. Well, I'm going to suggest we solve for y in terms of z. So that's going to give you 6y equals 1 minus 3z, which means that y itself is going to have to equal 1/6 minus 1/2 z. So y equals 1/6 minus 1/2 z. So z, of course, is z. Y itself is 1/6 minus 1/2 z. I'm going to suggest we put this y into the top original equation and solve for x. So this would turn into x minus 3 times 1/6 minus 1/2 z plus z is equal to that -2. Well, this should give you x minus 1/2 plus 3/2 z plus z equals -2. So then x minus 1/2 plus 5/2 z equals -2. And then we can simplify this one more time. We would get, let's see, if we move the constant term out of the left-hand side, so -2 plus 1/2, that'd be -3/2 minus 5/2 z. So you get x equals -3/2 minus 5/2 z, and then we just need to find parametric equations for the line. So let z equal t, always do that. So put in that value of t for the z on the x term, on the x equation, you would get x equals -3/2 minus 5/2 t, y equals 1/6 minus 1/2 t, and then z just equals t. So there are your three parametric equations for the line of intersection of these two planes. X equals -3/2 minus 5/2 t, y equals 1/6 minus 1/2 t, and then z just equals t. Alright, so that's it for this lesson. Next lesson is actually the very final lesson of the course. That's going to be finding the angle between two planes and then finding the distance from a point not on a plane to the plane itself. So I hope everybody has a great day. Take care.